Right. Hi everyone. Assalamualaikum and salam sejahtera. Okay, so we move on to tutorial 1.10. This is from example 1.10 of Stephen J. Chapman's book of Fundamental of Electric Machinery. Okay, so we'll be talking about this figure, which is starting of the linear DC machine. This is the model of the linear DC machine in starting condition. Okay, from the question, all of these questions will be based on the figure right over here. So firstly, let me draw this figure first. So we have a model of a linear DC machine. We have the source of linear DC machine, and there is a switch, resistance, and as usual, this part we will put on the conductor. So I will put the conductor. Actually, I have to write this. I will put the conductor. So I have the conductor placed in the magnetic field of B. So the direction of the magnetic field is directed into the page. B is 0.1 Tesla. The resistor is 0.3 ohm. VB, this is VB, is 120 volt, and there is current moving if we switch on. If we don't switch on, there will be no current. Okay, let me delete this first. Okay, because we don't switch on it yet. Cool. So this is the starting condition. What is the machine maximum starting current? So meaning that when we put on the switch, when we close the switch, what happens is, when we close the switch, what happens is this VB will supply the current that will be flowing through the resistor, and then through this bar. Current will be flowing from here to through the resistor, and then through the bar, meaning that suddenly the bar will be carrying current inside the magnetic field, and then the current will go back to the battery. So at the instant of the switch is closed, we can say that, okay, question number 1, what is the machine's starting current? When we close this switch, current will be flowing. That is the starting current. That is the starting current. So at starting, this conductor is not yet moved. So no movement of this conductor at the instant of starting, because when there is no current flowing in this conductor, meaning that it will be stationary. Okay, so we just want to find the starting current. So in this case, we can say that at starting, the velocity of the conductor is 0. So therefore VBL, which is the induced voltage, not yet produced. So meaning that at starting, this bar, this conductor is still stationary. So VBL is equals to E induced is 0 because V is 0. And then we can use the Kirchhoff voltage law based on the equation that we learned before. VB is E in plus IR. So we know that in this case, induced voltage is 0. So VB, here VB is equals to IR. We want to find the current. So we rearrange this equation to VB, I equals to VB over R. Then we substitute the values of VB, which is 120 volt divided by 0.3. So we have 400 ampere of starting current. So that is the situation at the instant of switch is on. Okay, we are not talking about the flow of current inside the, we are not talking about the flow of current inside the bar yet. No current. So no current. Still, we are not talking about current flowing in this bar that cause the force will be induced. No yet. Right? So how about the second question? B. Let me use numbering similar to the question. So this is 1, right? And then this one is number 2. So for the number 2, what is the steady state velocity at no load? Steady state velocity. The symbol is VSS at no load. Okay. So from starting, okay, what happened is when we start, the current will be flowing about 400 ampere, which is large current, large current. Then it will be flowing through this bar and go back to the battery. So when it flows in the bar, in the conductor, and go back to the battery, what happened is we have the current carrying conductor. All right, so we have the current carrying conductor. So as usual, if we have the current carrying conductor, which is the conductor is placed in the magnetic field, what happened is we can use the right hand rule to find the induced force, right? So in this case, using the right hand rule, we can say that there is force induced to the right. So there is force induced to the right, there is force induced to the right until some time when F in is equals to E in. The induced force it will start to move at V, okay, until sometime we achieve the steady state speed, and at that steady state speed of V, there is voltage induced across the bar. Okay, so we have the current carrying conductor. Firstly, it moves to the right, which is force will be induced, and then after it achieves a steady state speed with VSS, at that time the voltage also will be induced across the bar. All right, so at this instant we can say that, let me just write, show you again, explain. F induced will become 0 at steady state speed, and also at steady state speed no more current will be flowing, because if we redraw this, the graph here, if I draw the graph with I versus t, firstly we have starting the current, which is 400, right? So then the bar will start to move to the right, okay, because of the induced force, and then it will speed up. It will speed up, but at the same time the current will be dropped. But for the case of moving bar or conductor in the magnetic field, what happen is, if this bar is moving at V, what happen is it will induce the current, the voltage. It will induce the voltage up to some time. So let me draw another curve for velocity. Velocity will be increased up to some time. It will be steady state, and the current will be dropped up to 0. So this current is already 0, but at the instant of induced voltage equals to induced force, this is the steady state speed. So we can use the equation of VB is equals to induced voltage at this instant, and because this is the steady state, equilibrium, this VSS BL. So now we can find the steady state speed using VB that we have already know the value of VB over BL. So this is 120 divided by B is 0.1 and L is 10. Then we get 120 meter per second of VSS, steady state speed. So steady state speed is 120 meter per second. Okay, now the third question. Suppose a 30 Newton force pointing to the right were applied to the bar as shown in figure B. Where is figure B? Suppose that, let me write on this figure. Suppose that 30 Newton force pointing to the right were applied to the bar. What would be the steady state speed B? So for the third question, we apply force of 30 Newton. Applied force of 30 Newton to the right. So let me redraw is on this figure. So this time we know that this bar is still moving at steady state speed. At the same time, so still at VSS, at the same time we apply another force, which is F applied. So F applied is 30 Newton. So we want to find new steady state speed. Okay, so that is the question. So when we apply the force to this bar, initially it was VSS, but we apply force of another 30 Newton in the same direction. So there will be a new steady state speed. Meaning that we can say the final steady state final. We have the steady state speed final because we apply the force to the same direction of the initial steady state speed. So in this case, final steady state will occur when induced force equal to an opposite direction to the applied force. So after some time, there will be induced force to the opposite direction. So in this case, no more initial steady state speed, but final steady state speed, which is it achieve another state of equilibrium. Okay. So in this case, we can use the formula of applied force. Initially, the 30 Newton applied force until some time it achieve new steady state speed when Ff equals to induced force. Ff equals to F in, which is 30 Newton. So similarly, we can use ILB. So in this case, this is the current. You know that this current is current that produced because of applied force. So we have 30 Newton. I write it over here. So I equals to F in because F in equals to F, right? Divided by LB. So F in is 30 divided by L is 10, B is 0.1. So here we have 30 ampere. So this current, actually, this is the current that flowing back to the battery. Do you know what it means? Meaning that because of that force that we apply to the same direction of the initial direction of applied force of which is the right direction, right? What happened is it seems like the system is working like a generator, which is the current will be flowing back to the battery, which is the system is charging the battery. Okay, in this state I can draw it like this. So this is the bar, current is moving 30 amps back to the battery. Okay, so at this state we can say that the induced voltage at the bar is larger than the battery voltage. This is the generator action. So this is the generator action. So that is not the answer of the problem, because we want to find the new steady state speed in this case, right? So we want to find the new steady state speed, speed. So VSS final is how much, right? So now we have the information that this is the generator, meaning that this is battery. Okay, meaning that this system is now working as a generator. This part is induced E in, this part is VB. So in this case, in linear DC machine, we must always compare the magnitude of E in versus VB. Sometimes when VB is larger than E in, meaning that the system is working as a motor. If the induced voltage E in is larger than VB, on the other hand, the system is working as a generator. So in this case, this system is working as a generator, meaning that the current is flowing to the opposite direction of the clock, which is counterclockwise. So in this case, because E in is larger than VB. So when E in is larger than VB, using Kirchhoff voltage law, so we can write now, we can write the equation of Kirchhoff voltage law. If induced voltage is larger than VB, okay, we can write the KVL of E in is VB plus IR. So, okay, so we have the information already. VB is 120, and we just already calculate the current, which is 30 amps, and also we know the resistance already, 0.3. Then further calculate this, we get 129 volt. So meaning that this side is 129 volt. The VB side is 120. So induced voltage is larger than VB. Meaning that this is the state of charging. If I can further redraw this, suppose this circuit should looks like this lah. Sorry. So this circuit should looks like this. So charging the battery at 30 amps. Okay. And once we get the induced voltage, we already get the induced voltage here. We can further calculate what we want, which is the steady state speed. Okay. And the final steady state speed or VSS final is equals to induced voltage divided by BL. So V is E in over BL is the equation that we must know, right? So induced voltage now we have 129, B is 0.1 and L is 10. So we have also 129 meter per second for the new steady state speed. The original steady state speed was 120. This is the original steady state speed. Once we apply another force of 30 Newton, the system becomes generator. System menjadi generator, which is current will be supplied to the battery, which is charging the battery, and the system will achieve its new steady state speed of 129 meter per second. So that is the answer for question number 3. I want to rest for a moment. Let me pause this one. Okay, let's continue. Number 4. How much power will the bar be producing or consuming? So up to the third question, we know that this system is working as a generator, meaning that from the bar point of view, we can say that bar is producing power, not consuming power. Okay, from the bar side, we can say that it is producing power, meaning that the bar is working as a generator. So let me write the question. The question wants us to find the power, which is question number 4. Power of the generator lah. So we can say that generator power or power bar, P bar. So we can say that we can conclude that the bar is producing power because this is the generator action. Okay, so P bar is so we already know the induced voltage at the bar, which is 129, right, tadi? And also we know that the current flowing is 30 amps times I. So we can write it as 129 induced voltage times the current 30. So it is 3870 watt of power, right? So that is the question answer for the question number 4. That is the answer for question number 4. But I want to ask, how about the battery? How much power is battery is consuming? The power that the bar is producing is 3870. How about battery side? So we can also calculate the power of battery, which is voltage of the battery times the current. Also we get it 3600 watt. So you can see here the difference of power. This is the power supplying, this is the power at the battery. So this power is larger than the battery power, meaning that the system is working as a generator. Okay, now soalan 5, number 5, is the machine acting as a generator or motor? Yes, machine is working as generator lah. So we already know that. Now number 6, suppose 30 Newton of force pointing to the left. So we apply force to the left. Now we apply force to the left. What will be the new steady state speed be? Huh? Okay, now the case is, let me write it properly here. For you to understand, let me further write the situation in the previous question. Let's say we have the battery, we have the resistor. So this system is working as a generator, meaning that the current is flowing from generator, from the bar to the battery, and we have power at this side is 120. Power at this side is berapa? Power bar is 3870. Power battery, this is power bar, this is power back. Battery power is 3600, 3600. This is 3870. So actually from here we can also calculate the power loss. So we know I is 330 ampere. We can calculate P loss across this resistance, okay, which is using I square R. So in this case 30 square times R 0.3. So P loss is, where should I write it? P loss is 270 watt. That is the power loss. So machine is acting as the generator, there is a power loss. Okay, because we have resistance here, if the current flowing through that resistor, there will be some power loss. Also we can calculate the efficiency, efficiency, so and so on. All right, now question number 6, we apply another force of 30 Newton juga to the left hand side. So what happened is, let me redraw this. Now we have switch is closed, still closing. Then we have the resistor and the bar. Now at that state we have induced voltage. Now we apply force to the left hand side, which is not the applied force, but that is actually load, meaning that we apply load. initially the applied force was, the induced force was 30 Newton. Okay, then in this case we apply load of another 30 Newton. So this bar is moving at the steady state. Okay, at the steady state, and then after that we apply force. Uh, we apply force 30 Newton also. So let me write. Suppose F load is applied as in the figure. What would be the new steady state speed? This situation is like when we are using the hand drill. Okay, hand drill. We switch on the hand drill, then it will turns. It will turn, it will spin, it will spin the shaft. The shaft will be spinning, will be rotating up to the steady state speed, meaning that at the no load speed. Okay, then we are going to use that hand drill to make a hole, right? So when we apply that tip of the drill bit, no, what happen is meaning that we apply load lah. We apply load. So what happened that at that instant the steady state speed will be reduced. Will be reduced to a new steady state speed because of that F load. Okay. Because we want to tebuk lubang, we want to make a hole, right? So the situation here is like we apply F load lah to the induced force. Initially the bar was moving at steady state speed, but suddenly we apply force to the opposite direction. So at another instant we can say that VSS prime, which is new steady state speed. So new steady state speed if achieved when the induced force is equals to F load. So in this case we can infer that VSS prime is actually I don't want to use that symbol. It's actually less than the VSS, much more slower lah. So in this case we can use the F load equals to F induced. Induced voltage, induced force equals to load, right? Which is equals to ILB lah. Now we firstly find the current, new current because of that F load. So there will be new current. In this case, induced force is 30 Newton, L is 10, and B is 0.1. Again, current is now 30 amps. Sama jugalah. But this current is now flowing down through the bar actually. Which is, we can conclude that this situation is actually motor action. Alright. So this is motor action. Just now it was the generator action. So this time it achieved motor action. So that is the current. In this question, we want to find new steady state speed. So when we talk about motor action, so actually at this state now VB is much more larger and compared to the induced voltage. So this is motor action. VB is larger than induced voltage. So in this case, E in equals to VB using Kirchhoff voltage law again minus IR. For this case, actually, I would prefer use this sort of equation lah. Macam tadi juga, if in besar daripada VB, larger than VB, we put E in on the left hand side. But now, if VB is larger than E in, we put VB pula on the left hand side. So VB equals to E in plus IR. Okay. So in that case, we can rewrite this equation in the form of E in, which is VB minus IR. VB already know 120 minus I is 30 amps, sama juga macam tadi. And resistance is 0.3. Then we get the new induced voltage of 111. And once we get the induced voltage at load condition, so the final speed or VSS prime to VSS prime is using the same equation, E in over BL. Now E in is 111, B is 0.1, L is 10. So we get also 111 meter per second lah. So now machine work as a motor, which is the conversion of electric energy to the mechanical. Why mechanical? Because of the motion of the bar, right? Okay. So actually that is the answer for number 7. Is the machine works as motor or generator? So number 7 we can say that machine work as a motor or work as a motor lah, right? So I think I should write number 7. This is the I already write the answer for number 7. So the machine now works as a motor. Okay, so that's all. Okay, habis. Okay, that's all for the discussion of the tutorial 1.10, which is also you can refer to the example 1.10 that is written in the Chapman book. And in tomorrow's class we'll be continue on tutorial 1.14. We'll discuss on that question. Okay, that's all for today. So thank you so much and Assalamualaikum.